All right, this is the video notes for Unit 3, Day 7. This first page, as you'll see, we covered most of these notes in class, or at least the front half of this page. But in this lesson, we're talking about how to write function rules and equations for these different kinds of functions. And in class, we talked about that if we have a linear function, that means it has an arithmetic sequence of output. So these output side of our charts, okay, if we notice that there's an arithmetic sequence, remember arithmetic sequence means we are having a common difference. You add or subtract to get each new term. If that's the case, it's linear. And we can always write linear functions in this form. It's kind of like y equals mx plus b. Only we use function notation. F of n or f of x equals m n or x plus b. So we went through some examples on how to write function rules in two different forms. This form is called the explicit form. The normal form you're used to is called explicit. Explicit uses function notation like this, and we just write an equation, okay? But then we learned this new form called recursive form. Recursive form uses two lines. The first line is always just a sub 1 equals the first term, okay? That is always just your first term. And then a sub n is written this way, okay? We're just saying each new term equals the previous term, and the previous term is written as this expression. Okay, that's the part that we use to represent the previous term. Rather than write out the word previous term, we use this notation. We read it as a sub n minus 1. So we take the previous term and then we add the common difference to it. If it's a positive common difference, it's just a plus. If it's a subtracting every time, you write it as minus. Okay, so that's how we write explicit and recursive forms for linear functions. Now, if we turn to the back, we're going to finish our video out, and we're going to turn to the back, and we're going to look at how to write function rules when we have exponential functions. Okay, we're dealing with exponential functions now. Okay, and so I've given you two examples that we're going to follow along, and I'm only going to show you the explicit form. So we're just writing using function notation. So each of these, our answer is going to be f of n equals something for both of these. Okay? So what we're going to do as we go through this, we are going to kind of identify some of these questions as we go through. So in example 3, you'll notice that we start with our first term, evaluated at 1, is 4. Then our second term gives us 16, our third term is 64, and so on and so forth. And if you notice, we're not adding the same thing every time. To go from 4 to 16, I would have to add 12. But then to go from 16 to 64, I'm adding 48. Okay, and so we're jumping up by adding a lot more each time. So it's not a linear function. This is not an arithmetic sequence. This is a geometric sequence which will have a common factor. Okay, our common factor every time, you'll notice that we can multiply by a constant number every time. 4 times 4 is 16, and if I do 16 times 4, I get 64, and then 64 times 4 is 256. So we're multiplying by 4 every time. And if you can't see what you would multiply by, just go backwards and do division. Do 16 divided by 4, you get 4. 64 divided by 16 equals 4. 256 divided by 64 equals 4, and you get that common factor every time. You can use your calculator to help check that. Okay? And so we're going to write our function based this way, okay? That common factor is always the base of our exponent for our exponential function. That common factor is always your base, okay? And we always take that to the nth power. Now in this case, 4 to the first power is 4. 4 to the second power is 16. 4 to the first, 4 to the second, 4 to the third, and 4 to the fourth. And so it really works out that this is exactly what our function is. There's nothing extra here. It's just f of n equals 4 to the nth power. Okay? But when I go over here and I try and do this, let's identify our common factor again. As we identify our common factor every time, we look at what do I multiply by to get my new term. Okay? 6 times 2 gives me 12, times 2 gives me 24, times 2, so on and so forth. So we're going to write our function rule using a base number of 2 to that nth power. But then if you look, 2 to the first power is just 2. That's not 6, okay? So I need it to equal 6. Well, like we did with linear functions, we're going to go back a step, okay? We're going to go back to our 0 term when n is 0. And what we notice here, when I go back a step by dividing by 2, 6 divided by 2 gives me 3. So at my 0 term, I have a 3. So when this power is 0, I still have an answer that equals 3. Okay, so what you'll notice is all I have to do to turn that into that is to take this 0 term and write it as a coefficient of my power. Because now if I plug this in, if I do 2 to the 0 power, that's 1. Remember, anything to the 0 power is always 1. 1 times 3 is 3. 2 to the first power is 2. 2 times 3 is 6. 2 to the second power is 4. 4 times 3 is 12. And you notice that that fits the pattern now. So this would be our function rule. 3 times 2 to the n. Just like in example 1, or sorry, example 3, the one we just did here, it was just 4 to the n. Okay? And so let's talk about these questions. Is there a common difference or a common factor? Well, on each of these, we're going to split this in two and talk about each one. In this first example, there was a common factor. Okay? And that became our base number for our power, for our exponent, because these are exponential functions. Okay, here we had a common factor as well. So if we look at our pattern of output and we notice there's a common factor or common multiple here, then I know it's going to be exponential, and that common factor is the base in our formula. Then we looked back and we looked at what is the function evaluated at 0, okay, specifically on this one. So if I go backwards, all right, the function evaluated at 0 here would be divided by 4, that's just a 1. So in this case, it's a 1. When the function evaluated at 0 is a 1, I don't need to write anything in front of my base. But this time, the function evaluated at 0 gave us 3. And so these are the two parts that we get in exponential function rules. Okay? If a function is exponential, then this is our function rule, and it's always going to follow this pattern. The function is equal to a times b to the x. B is the common factor, or what we call the growth rate. That's another term we need to identify. And then this a value is the function evaluated at 0. Okay? So let's try some extra examples. All right, we're going to write an equation for each of these functions or sequences. Okay? So remember, if it's exponential, we're always following this pattern. F of n equals a times b to that nth power, where a is our initial term evaluated at 0, and b is the common factor. Okay, so let's work out our extra examples. Okay, we're going to work out example 1 first. Okay, this would be our first term, then our second term, and our third and fourth and fifth and so on. So even if they just write out a list, they're giving you these values. So this is like your n, and this is your f of n. Okay? And so what I'm going to do is I'm going to come over here, and I'm going to put my number 1 right here where I've got some room to work with this. The first thing we want to look at is that pattern of outcome from 7 to 11 to 15 to 19 to 23. I want you to think about this. Is there a common difference or a common factor? Well, in this case, there isn't a common factor, but there is a common difference. If I took 11 minus 7, I'd get 4. And 15 minus 11 is also 4. And 19 minus 15 is 4. So the common difference here is 4. Okay, so this is linear. So I'm going to follow this pattern. F of n equals m times that n value plus b. Y equals mx plus b. Excuse me while I answer the phone. All right, sorry about that interruption. So if it's linear, which this one is, we're going to follow this pattern where, remember, m, I'm going to flip back over, we're just going to follow that. M is always the common difference. So that we realized on this problem, the common difference was 4. So I can just start filling this in, that our function evaluated at n, is always going to be 4 times that nth value, or 4 times the number of term that it is. But then I have to find the initial value. I got to make sure, because if I just did 4 times 1, that's 4. But my first term should be 7. And 4 times 2 would be 8, not 11. You get the idea? So what I have to do is go a step backwards to if n were 0. So I'm going to do the opposite of plus 4 each time. Okay, instead of plus 4, I'm going to do minus 4. And 7 minus 4 is 3. So that tells me my b value. And so this ends up being the function rule in explicit form for this function. All right? We're going to try number 2. And actually, I'm going to kind of guide you through this, and I'm going to have you try these on your own and bring those to class. So if I look at this, I go from 2 to 8 to 32 to 128. This is your first clue that this is not linear, because the numbers increase more rapidly each time. We get bigger very, very early in my sequence. I get all the way to 500. So it can't be just by adding or subtracting. In this case, adding because it'd be bigger. But it can't be that. So I have to look at what I would multiply by. If you're not sure, we can always just take 2 terms in a row, take the one that's to the right, and divide by the one before it. 8 divided by 2 is 4. 32 divided by 8 is also 4. And you notice very quickly that the common factor here is 4. So for number 2, this has a common factor, which is 4. So this is not linear, this is exponential. Since it's exponential, I'm following this pattern. Okay, so my f of n is equal to some initial value times the scale factor or growth factor of b to the n, or b to the x. Okay, that should be an n there, not to confuse anybody. Okay? So I have to realize, remembering that b is the common factor that I just noticed, the common factor is 4. So for my answer this time, it's f of n equals something times 4 to the n. But I have to find that a value, that initial value evaluating this function at 0. So I'm going to go back a step again. Okay, I'm going to go back a step. Instead of multiplying by 4 to go forward, I'm going to divide by 4. 2 divided by 4 is a fraction. That's okay. We're going to get fractions. 2 divided by 4. But that fraction reduces to 1/2 or 0.5. It's best to write that as a fraction. So I'm going to write it as a fraction, 1/2. And that's my answer for number 2. So what I want you to do, I want you to look at numbers 3 and 4. Okay, I'm going to kind of get you started. I'm going to tell you this. Number 3, if you look at how the numbers increase very quickly, or as you go down the list, they get bigger and bigger and bigger until we're in the 9,000s, that is your clue that this is exponential. And then over here on this example, as my numbers are increasing, I'm only going up by a 0.5 every time. Okay, so that's linear. I'm adding. I'm just adding 0.5 each time. So I've already kind of gotten you started. I want you to write the function rules. Okay, on this one, we're using this form. And on this one, we're using this form. Okay, we're looking for m and b here. We're looking for a and b here. We use b, but they mean different things, so don't get confused by that. All right, hopefully you get these notes taken care of, and when you come to class, we are ready to take a look.